Welcome back. Welcome to your video under introductory analysis. And in this video, we are going to look at limit of sequences. Limit of sequences. Now you know what sequence means. You know also what series also means. Alright? Very good from your previous knowledge. So now, here we are saying that sequences are denoted by a subscript what? N. That means that it's like they are a function which is in terms of what? N. Alright? We can get, for instance, a of n is equal to n squared plus 1 over n. It can be this or all to the power of n, or it can be that. And we are saying that the n is equal to 1, and you know that this sign represents what? Infinity sign. Alright, so this means that we can plot to get these sequences. You first put if n is equal to 1, then what will you get? If n is equal to 2, what will you get? If n is equal to 3, what will you get? So by doing that, you will be able to generate all these what? Sequences. Alright? You'll be able to generate all these sequences, and it's from 1 to what? Infinity. Alright. So that is what sequence means. And when you add them, it becomes a series. If we are saying that 1, 2, 3, 4, is or are sequences, that means that the comma there is making it representing what? Sequences. But if we remove the commas and bring addition, it becomes series. It becomes series of what? Numbers. Alright. So definition. Now, as I said, the whole of this course is all about theorems, definitions, and all that, and a lot about solving more questions also. So the limit of a sequence a of n is a, and it's written as, what we are saying is that when we take the limits of this sequence, where n represents infinity, the result is going to give us what? A. This A we are having here can be any number. It can be 2, it can be 3, it can be half, it can be any of it that you can. So now, if in case you have search and you are to prove whether yes, you are going to do a lot of proving, and you are to prove whether this equal to this is true, there is a need for you to state the definition first. This is the definition for any sequences. Alright? For any sequences, that is the function in terms of what? N. If given any epsilon, this is called epsilon. If given any epsilon greater than 0, there exists a number. And not just any number, but there exists a natural number, where the natural number is in terms of what? Epsilon. Such that a of n minus a is less than epsilon. What we mean is that when you set this to this side, you are going to get a of n minus what? Minus a. And it's going to be less than what? Epsilon. Where small n is greater than the capital N. If small n is greater than the capital N, then that means that we can reduce this. Watch. Don't forget what we have previously done. When you take the inverse of this, which is 1 over n, and you take the inverse of this, which is 1 over capital N. This sign will change. This sign, because you are taking the inverse of 8, this means that you want to reduce the N. This means that you want to reduce the capital N. And the sign will now change. So here, the capital N is greater than this, but here, you are going to get it to be what? Less. Is that clear? Alright. It's going to be interesting. It's going to be an interesting course for you in this video. Alright. Not only this video, but the whole of it. Okay. So, that is that for that. Please, don't forget this definition. And in fact, this definition has to stick off head. And because anytime nobody will ask you to state the definition for this. But before you solve any or before you prove, you have to write the definition. You have to write the definition. If not, you will lose marks for that. Good. Because this is giving you the idea in proving of whatever question you are going to beat. Very good. So let's look at what we have here. We have to prove that the limit. In fact, all that we are going to do is just simple. We have to prove that the limit of a function, and not just any function, but a sequence of what? A function. And I want to emphasize on that for some reasons. The limit, and we don't call it lim, is the limit of a function 1 over n as n approaches infinity is equal to 0. So you start, in fact, I will not state it, but you have to state it before you start solving. So I have it here already. So I will state everything here. Alright? I will state everything here. But don't forget that when you are done, note that A of n is representing 1 over n. Hope you can see that. The A of n is representing 1 over n. And the 0 here is representing what? The A. Looking at it from here, you can see that. Alright. So from what we have stated, it means that here 1 over n minus what? 0. Because it's saying that you will send this one to this side. And when you do that, then you bring less than what? Epsilon. Less than what? Epsilon. Alright. And now you know that with this, you are going to get 1 over n is less than epsilon. Very good. Very good. And this 1 over n, what is less than epsilon? We know here that from here that this epsilon is the same as 1 over what? That is capital 1 over what? N. Capital 1 over n. So this is going to give you 1 over n is less than 1 over capital N. Alright? 1 over capital N. So here we are. Then you choose. Don't forget. Then you choose. You choose capital N. You choose capital N to be equal to 1 over epsilon. Then you choose capital N to be equal to 1 over epsilon. Now, that is making sense. That is making sense because if you are saying that epsilon there is equal to 1 over capital N, let's watch something. Then that means that capital N will be equal to 1 over what? Epsilon. And it's true. And it's making sense. Alright? Very good. Because we are saying that that natural number is in terms of what? Epsilon. So we want to get rid of all the what? The n. So that we can replace that by what? Our epsilon. So by substitution, now don't forget that this is what we have transformed to this. Alright? So if this is less than this, then we have choose n to be equal to 1 over epsilon. And I have explained to you here that if you are saying that 1 over n, this side is less than the epsilon, then the epsilon is 1 over capital what? N. So by substitution, epsilon 1 over, don't bring this side again. Alright? And the capital N is what? 1 over epsilon. And you know that 1 over epsilon is just going to be less than what? Epsilon. Very good. Very good. So, since our output now is less than epsilon, that means that the given question is proved. The given question is proved. I hope it's clear. Alright. Let's look at our second example. Alright, welcome back to the second question. Now we have to prove that the limits of this as n approaches infinity is equal to 2. Very good. Very good. Now, what this means is that we have to show how this limit equal to 2. Yes, we know when you solve this from your calculus 1, when you solve this, you are going to be 2. Yes, we know that it's going to be 2. But here, we want you to show us or prove to us whether this is equal to 2. So as I said, it's the function is in terms of n. Alright? So this means that it's a sequences. It's what? A sequences. Alright? So you start with the definition. If given any epsilon greater than 0, there exists a natural number. It should be up there. There exists a natural number. You see that? Such that less than epsilon wherever how you can see that? Very good. So you do like that, then you start. We are saying that a of n minus what? A will be less than what? Epsilon. Alright? And you know that the a of n is equal to 2n squared plus 1 over n squared plus 3n. Hope you can see that. Very good. And the a here represents the 2. The a here represents the 2. So what we mean is just simple as this. 2n squared plus 1 over n squared plus 3n minus 2 is going to be less than what? This absolute sign is very important. What we mean is that, you know what this means? This means that when we take the absolute of all these, the result is going to be less than what? The epsilon. Alright. Very good. So, from here you can choose to bring the sign. You can choose to bring the epsilon or choose not to bring it. So here we have 2n squared plus 1 over n squared plus 3n minus, here is minus 2. So we want to achieve the same what? Denominator. So we have to multiply this. We have to create and what? Destroy. So we know that this and this cancel out and you get 1. So it's the same thing. Alright. Then you see what we have here. That is 2n squared plus 1 minus 2n squared plus 3n. All this over n squared plus 3n. Very good. And this, the numerator only is going to give you 2n squared plus 1 minus 2n squared minus 6n. All this over n squared plus 3n. And having this, we can see that this will cancel this. So we are going to get, very good. So we are going to get 1 minus 6n over n squared plus 3n. Here we are. Let's see what we are going to do here. Oh, I don't want to print this. As I said, always the moment you write solution, first write your definition, then you start solving. So that is that for that. Don't forget to always write your definition. I hope I can clean up. Alright? I won't be writing it again. So I can clean up. Very good. So something is going to happen here. Alright? Now we are saying that, please, algebra. We are going to take the absolute of this. Alright? And we know that in absolute, negatives don't matter. We don't care about negatives. So we can write this as 6n minus 1. Yes. Watch. Because if you have 1 minus 6n and you negate both sides, oh sorry, and you negate it, you're going to get negative 1 plus what? 6n. Alright? Very good. Because this is plus or what? Minus. So when you apply that, you don't need to bring the absolute sign what? Again. Because this means plus or minus. Alright? So when you negate it, you don't need to bring the absolute sign again. So we are going to have 6n minus 1 over, and here we write what is there, and that is n squared plus 3n. Now listen. For the epsilon to be bigger, because we know that here this is less than what? Epsilon. That means that the epsilon is greater than what? This. Don't forget that I told you that you can repeat the epsilon, repeat the epsilon, repeat the epsilon, repeat the epsilon, repeat the epsilon. Alright? So what we mean here is that we can write it down. For the epsilon to be bigger, we need to drop. For the epsilon to be bigger, we need to drop negative 1 over 3n. We need to drop whatever is here and focus on only the one here. That is for the epsilon to be bigger. We need to drop that part. Alright? In the denominator and the what? In the numerator. So with the numerator we drop the negative 1, and the denominator we drop the 3n. Very good. And it's just simple in this way that you see this is greater than this is greater than this, alright? Because you put values here. We have here to be squared, and we have here to be power 1. So we are going to drop this side. So we get 6n over n squared less than what? Epsilon. And here we get 6 over n less than epsilon. Now, don't forget, here is where we are going to do that interesting thing. Watch. What we mean mean here is that, now, don't forget that this 6 here is a constant, alright? And from the definition, we know that 1 over n is less than 1 over capital what? N. So from our previous example, we established that when you get to this side, the epsilon is 1 over n. Alright, the epsilon is 1 over n. But please, it's not always the 1 on top. The numerator is not always 1. It depends on what is on the left hand side here. So looking at what is on the left hand side here, we don't need to write 1 here, but rather what? 6. Very good. And here 6. So if 6 over n is less than 6 over capital N, this is how it's going to be when you link this to the general definition. Therefore, we choose epsilon to be equal to 6 over capital N. Alright? And if you choose epsilon to be equal to 6 over capital N, then we get 6 over small n less than 6 over capital N. Very good. Now, if this is true, then we can do the substitution of what? The capital N. Because if epsilon is equal to 6 over capital N, then capital N, I hope you're going to see from there, capital N will be equal to what? 6 over epsilon. Yes. Yes. That is so. So here we are going to replace the capital N by 6 over what? Epsilon. By 6 over epsilon. So we get 6 over. So the whole of this capital N is equal to what? 6 over what? Epsilon. Please, here, some people normally bring less than. If you bring less than here, it's wrong. You can bring equal to sign there. So this is equal to 6 over, this is what? 6 over epsilon. 6 over epsilon. And you can see that this is the same as 6 over 1. And it's multiplying this. So in division, the reciprocal comes in. So we get epsilon over 6. This and this will cancel this. So we get it to be what? Epsilon. We get our final answer to be what? Epsilon. So this is going to be less than epsilon. It's going to be less than what? Epsilon. Let me bring that. Less than epsilon. This just implies that this is less than epsilon. And now, since we have our results to be epsilon being the greater, it means that we have successfully reached our proof that this is equal to 2. Oh, it's not difficult. Not difficult. Not difficult. It's never difficult. Is it the algebra or the absolute sign? You know when the absolute sign will vanish and all that. Very good. Let's move on to our third question. Yeah, I have some interesting questions here. Let me quickly rush through my notes. Good. One is here. Let's look at this one and you will love it. Prove that the limits n squared plus 3n, all this over 2n squared plus n minus 1 is equal to half. So you start with the definition. I beg you, start with the definition. If given any epsilon greater than 0, there exists, alright, you can write it like this. If given any epsilon greater than 0, there exists, n in terms of epsilon, alright, which belongs to all natural what? Numbers, such that in a short form you can write it like this, such that a of n minus what? A is less than what? Epsilon. Is less than what? Epsilon. When 1 over n is less than 1 over capital N, then you go your way. Very good. That is that. So here we start from what we have here, that a of n minus a is less than epsilon. So here you know this is n squared plus 3n over 2n squared plus n minus 1 over 2 less than epsilon. Alright. So as we normally do, we want algebra to attain the same denominator. We have to do something. You know that this is half, alright? Very good. So let's look at something. What will we do to achieve the same denominator? Alright, so here what we are going to do is just simple. Let's repeat the same thing like what we did in the first part. 2n squared plus n minus 1. Alright, very good. Two n squared plus n minus 1. Alright, so here we know that when this and this cancel out, you get 1. So it doesn't affect anything. Alright, this is just small algebra. Good. But don't forget that we have half here multiplying the whole of this. Okay? So half is here. Now we are going to do something. Watch. This is the same as what is here. Then what we have down here, we multiply this by what? By repeating this on top and what? The down. That is both the numerator and the denominator. Now, we want to achieve the same what? Denominator. But this is the case that 2 is multiplying this. That will not help us to achieve it. So we have to create and destroy here. So it's like this. Then, let's create in such a case says that we can also multiply here by 2. And if that be the case, then we have to destroy it. Because this divided by this is 1. Alright. So here we get 2n squared plus 6n minus 2n squared plus n minus 1. All this over. Hope you can see what is there. All this over 2n squared plus n minus 1. Very good. So less than epsilon, you can repeat it. Okay. Here 2n squared plus 6n minus 2n squared minus n, and then again 4. Hope you can see that. And it's 4n squared plus 2n. 4n squared plus 2n minus 2. Very good. So that is what we have there. This will cancel this, and we are left with 6n minus n. We get what? 5n plus 1. All this over. And what do we have here? 4n squared plus 2n minus 2. Less than epsilon. Very good. This is the interesting part. So here we choose to remove the absolute because the absolute means plus or what? Minus. And here we choose the positive one. Very good. Because the coefficient here is positive, the coefficient here is positive. So we don't worry ourselves again. But if we have, let's say, 1 minus 5n, that means that we are going to have something like this, which will not help. So that in that case, we choose the negative. Don't forget that we are doing analysis, so this is just analysis. Alright. Now, here, in the same way, for epsilon to be greater than this sequence, the epsilon to be greater, then we have to reduce. We have to reduce this and reduce this. So we reduce the whole numerator to be 5n over, and also reduce the denominator to be 4n squared. So that is what we reduce for it to become. Alright. But in the reducing, we can increase this by 1, whereby it won't affect anything. But we can also choose to maintain it as such like this. For me not to apply too much analysis to confuse your understanding, let me leave it as such. So this is less than what? Epsilon. But here we are going to get 5 over 4n less than epsilon. And we know that the epsilon is, now the epsilon, is it going to be 1 over capital N or what? Now, let's see. Let me clean this part. So here simply, here we choose, or let's repeat this part first. 5 5 over 4n is going to be less than this small n we just change to capital N, that is 4. So 5 over 4 capital N. Alright? Very good. Now, if epsilon is equal to, just repeat the same thing, but let's do capital N, that is all. If epsilon is equal to 5 over 4 over capital N, because that's what we are used to replace it. Then, to get capital N, we are going to get capital N, we get 4 capital N epsilon is equal to 5. Alright, so you can see that capital N is just going to be 4 epsilon, this 4 epsilon. Alright, this will cancel this will cancel that. So we get capital N to be this. Now watch 5 over 4 epsilon. It's not the same as, watch, it's not the same as this. If I were you, I won't be doing this. If this is equal to this, then make capital N a subject. I will just say that choose epsilon to be equal to 5 over 4 epsilon, sorry, choose capital N to be equal to 5 over 4 epsilon. That is all, and that's exactly what we are getting here. Alright, but don't worry, use what you think it will be familiar to you. So here, 5 over 4 times capital N is what? 5 over 4 epsilon. This will cancel this. And here, simply we get this to be epsilon. Alright. This is not the first time meeting something like this. So, know what to do with 5 over 1. I won't be doing it again. 5 over 1 is the same as here you get epsilon over 5. This will cancel this. So you get it to be less than what? Epsilon. Alright. So now it's proved. Now it's proved. Beautiful. Beautiful. Now it's proved. Very good. Let me see if I can get 2 more questions.